Hello, good evening. Am I audible to you? Hello.
Yes, sir.
Yeah, thank you. So we'll start now. So my name is Ranjan Bora and I am the TA. Okay. I am the TA in this course, Biomechanics of Joints and Orthopaedic Implants. And this course is instructed by Professor Sanjay Gupta from IIT Kharagpur. And I have been taking the tutorials every week on Friday, Friday on every week, and from the 6 p.m. to 8 p.m. And the previous week tutorials I have uploaded in my YouTube channels, and the links to those channels you can find in the NPTEL website. The web page of this course in the NPTEL website. And today is the week 5. So first I will solve the assignment from week 4, and after that I will explain some concepts from week 5, like concepts related to stress strain and principal stress principal strain, and I will solve some numerical problems using those concepts. So first I will solve the assignment from last week, which is week 4. Okay, the first question was link segment model will help. So you can type your answers. If you have submitted, then you should know which option will be correct. What is the right answer for this question? Yeah, A is the right answer. So you can see, like in the link segment model, what we do, we represent the anatomical model using some link model, and means we separate out the links, like we separate the foot and separate the tibia bone and separate the femur bone, and we do the analysis, like first we calculate the reaction forces at the ankle joint, and those reaction forces then used in the tibia to find the reaction forces in the knee joint. And like this, using this approach, we estimate the joint moment and reaction forces at any joint. So, and the second question was, among the following, which body segment have highest mass? What is the answer?
A.
No, not A. No, it is pelvis. Like in the slides, there is one chart which is given. Like you can see this column. This column represent the segment weight divided by total body weight. So here abdomen, you can see, like for abdomen it is 0.139. For pelvis it is 0.142, and for foot it is 0.015. For thigh it is 0.1. So highest is for pelvis. So option C is correct. Okay, next question is forward dynamics method. What is the input for forward dynamics method? Yeah, it assumes the muscle excitations, like we provide the muscle excitations, and using this method we estimate the joint kinematics and muscle forces. Okay, then we can use this muscle forces and kinematics data in the static optimization method for the optimal muscle excitations. So option A is correct. And which one is a kinematic variable? Like what are the kinematic variables? Yes, displacement. So what are the kinematic variables? Kinematic variables are involved in the description of the movement and are independent of the forces that cause the movement. They include the linear and angular displacements, velocities, and accelerations. So in this question, option D is correct. And postural stability increases with the So first we'll see like what happens to the postural stability if the height of the COZ decreases. So you can see this stability means stability is represented using this triangle. So here D1 represent the step means the width of this. If we assume this is one foot and this is another foot, so D1 represents the half of the width between the 2 foot when we stand on the ground. And what is H? H represent the distance of the COZ, center of gravity, from the ground. So like you can see this using this relation, theta is equal to tan inverse D by H. So if the height of the COZ decreases, that means if H1 decreases, what happens? If H1 decreases, then this bracket means the parameter which is inside the bracket d by h, it will increase. And if this increases, then theta will increase. Okay. So what does it mean if theta increases? So theta increases means to cause means to initiate the instability, we need to rotate with a theta which is greater, with a higher value of theta. So means and the when stability will decrease when theta decreases. So yes, position of COZ is constant, but means this is comparing with different. No. If the height of the subject increases, let's say there is a person with 3 feet height, and there is a person with 6 feet height. So for this 6 feet height, the height of the COZ will be more compared to this person 3 feet. So means this is the comparison between these two. So if the height of the COZ, and we can the COZ height is not fixed. Okay, if we are standing, then it is fixed. Then if we bend forward, the COZ will means height of the COZ will also bend forward. So it is not fixed. Okay, so we can change the position of the COZ according to the activity we perform. So now I am in the sitting position. So the COZ height is COT height is at the level of my chair. If I stand up, then COZ height will increase. So COZ height is not fixed even for a person. So this question is about those conditions, like what happens if the COZ height means what happens to the postural stability if the COZ height changes. So we saw that if the COZ height decreases, then postural stability increases. So is it clear, or do you still have any doubt? Do you have any doubts, Samart? Okay. So next we'll see means the base of support. So what happens if the base of support increases? So means if the base of support increases, then D will increase. So for D will increase, then theta will increase. So the stability will increase. And also if the weight of the object increases, then it will be means it will be difficult to uh, displace that object. So in this case, all of the options are correct. Okay, next question is joint bone on bone forces are. What are the causes for bone on bone forces? Yeah. So you can see now in case one, like this 90 Newton is the weight of this lower bone, and now the muscles are not in the excited state, means muscles are not active in this case one. So they are producing like 45 in both the muscles in the upward side. But when the muscles are excited, then they will produce means they are producing greater than the 45. They are producing 75. So to balance out the additional 60 Newton, there will be one force that will act on this bone on bone contact. So it is generated because of the activity of the muscle.
Sir, is the lower bone is being pulled, right? Not the upper bone.
Yeah. Lower bone is pulled. Yes.
The arrow is showing downwards, like 60 downwards and 90 downwards. What does that mean?
90 is the weight of the lower bone. This is weight of, and 60 is the bone on bone force.
So that means
60 is producing.
lower bone is exerting force on upper bone, right? So the arrow should be upward.
No, if the lower bone is exerting force on the upper bone, then it will be downward. Means this 60 Newton is not producing because of this lower bone. This 60 Newton is producing because of the excitations of the muscles. So muscle forces are acting in the upward direction. That's why this 60 Newton is acting in the downward direction in the upper bone.
Okay.
Okay. Okay. Next, ankle dorsiflexor muscle moment will be maximum at when the ankle dorsiflexor muscle moment is maximum. Yes. So you can see this is the this is the gait cycle, and this moment is for dorsiflexion, and this upper moment is for plantar flexion. So means at the starting, at the heel strike phase, it attains a peak. Then for the dorsiflexion case, so it is option A is correct. And next is direction of angular velocity and acceleration of sway during quiet stance depends on. What is the answer? No. Means check if it depends on position of COG, position of COP, or all of the above. Yes, it depends on all of the above. So you can see this direction of angular velocity and acceleration means this direction of omega and alpha. So position of COG means this this W position. So there is one relation like from the ankle joint, P is the distance between from the position of COP and the ankle joint, and one distance is missing here. D is the distance with, oh sorry, it is given, G is given. So G is the distance between ankle joint and the direction of means direction of weight which will act through the COG. So and the what happens if this W dot G is greater than R dot P? In that case, this direction of acceleration is clockwise, and if it is less than R dot P, then direction of acceleration is anti-clockwise. So it depends on position of COG, position of COP, and also these weight parameters. So it depends on all.
But they have mentioned that it is a quiet stance. So why we are taking the angular velocity into consideration, not the normal velocity? Nothing is rotating, right? So why angular velocity? There is no rotating component.
Yeah. So even if it is quiet stance means quiet stance means consider any position like we are standing on the ground and we are not doing any kind of motion. Means we cannot stand like we cannot stand in which where this alpha is 0 and omega is 0. So this is the impossible case. Okay, means whenever we stand, there are some alpha and there are some omega. So that's why.
Yes, sir. But like omega is angular velocity, right? And for angular
Yes.
velocity to exist, things must rotate around some kind of axis. Like then only we consider angular velocity.
Yeah. Yes.
But there is no rotating like around the axis. There is no component rotating. So why they have considered angular velocity? Or is
Yeah,
there a
because see in this position, like when this is standing, then here summation of this is summation of Fy is 0 because this W equal to R. Okay. Means this reaction force R will be equal to weight of the person, which is W. And but here summation of M not equal to 0 means moment exists. That's why since there is moment, that's why we are considering this angular velocity and angular acceleration.
okay, sir. That's
Okay, is it clear?
yes, sir.
Okay. Okay, next question is physiological cross section of muscle increases with. What is the answer? Yes. So you can see this is the relation for physiological cross section area. Here Alpha is the penetration angle, M is the mass of muscle fibers, D is the density, and L is the length. So we know that for cos alpha, like we all know, when alpha increases, then cos alpha decreases. Okay, this is 0 and this is 90. So in other way, when alpha decreases, then cos alpha increases. So that's why when alpha decreases, then cos alpha increases, and this physiological cross section of muscle increases. Next question, mechanical advantage of muscle is influenced by. Yeah. So means it mechanical advantage means we are getting the momentum for that muscle. We are getting some more momentum. So means when means what will happen if we get more momentum? Like consider this joint and there is one muscle here, and there is another muscle here. So for the first muscle, this momentum is A, and for this second muscle, this momentum is B. So because this momentum is more for the second muscle, so for producing any moment, like we need to produce this moment M. What is moment? Moment is force multiplied by this momentum. So in the second case where B is more, when B is greater than B is more, in that case, the muscle has to produce less force compared to this case. So muscle force in case B is less compared to muscle force in case A. Okay, because this momentum for B is more than the momentum for A. So this is called this mechanical advantage.
Sir, does the like tendon also counts as a force producing element here? Because tendon itself is not producing any force. So shouldn't momentum extend up
Yeah.
to the muscle itself?
Yes, right. But what means tendon is there to connect the muscle with the bone. So it is not a force producing element. Like the muscle produces the force, but because of the presence of the tendon, we get this. The momentum is more, means compared to the case in which there is no tendon.
Yes.
Okay.
Yes, sir.
So that is the reason. So in that case, all of the above is correct. And next question is, which method is used to calculate the joint moments and forces from the known information of kinetics? No, it is inverse dynamics. Do you have any doubt in this question? Like from the inverse kinematics, we get the joint angles. Means all the kinematics information we get from inverse inverse kinematics. And from this inverse dynamics, we get joint moments and force. Okay. And the balance of human body depends on the position of center of gravity and like we have seen it just now. Yeah, center of pressure. Anthropometric variable refers to data related to what are the anthropometric variables. So joint angle is, I have just said that joint angle means kinematics. Yeah. And joint forces are the kinetic parameters, and anthropometric variables means this segment masses, inertial parameters. So these are the parameters which comes under the anthropometric data: limb segment mass, center of mass, and mass moment of inertia. Now the contribution of each muscle force and distribution is solved using which numerical approach? I have also discussed this question few minutes back. No. Contribution of its muscle force and distribution is solved using static optimization. So just now I did show you this chart. So what does this static optimization do? Static optimization, it optimizes the sum of the muscle activations, and by constraining the force produced by each muscle less than the maximum isometric force for that muscle. So in the slides there is detail about the static optimization.
Sir, but forward dynamics also takes muscle force as input. Forward dynamics.
Forward dynamics. Okay, I'll see what was the forward dynamics. It does not give the distribution. Okay, like the distribution of muscle force. It only gives the muscle forces. Means but static optimization gives the distribution for each muscle.
Okay, sir. Understood.
And next is, which one of the following is not a kinematic variable? Yeah, ground reaction force is not a kinematic variable. So again, the kinematic variables are the limb segment angles, joint angles, linear and angular velocities, and linear and angular acceleration. And what is the angle between the long axis of the muscle and the fiber called? Yes, this is the Pearson angle, alpha. So the long axis of the muscle and the axis of the fiber. So option B is correct. And during normal working activity, how many peaks of reaction forces are
Sir,
observed in angle?
does all muscles have pennation angle, or only some muscles have pennation angle? Is it a specialty
Yeah,
of muscles?
yeah, all muscles have pennation angle, but there are some muscles for which the pennation angle is 0. Means the muscles fibers are oriented along the axis of that muscle. But there are very few muscles for which the pennation angle is 0. Most of the muscles that there are some pennation angles.
Okay, sir.
And what is the answer for this question? Yeah, 2. So can you tell me at what percentage of gate we are seeing those 2 peaks?
First is at, I guess, 10%, then 50%.
Yes, yes. One is here and another one is around here.
It was a guess though, if you want to correct me.
Sorry, what?
It was a guess. I actually did not know that there were 2 peaks. So if you want to correct me.
Yeah, we are seeing only these 2 peaks, right?
Because I thought because it is originating from 0, that it might not be a peak. And 80 to 100 might be another peak. That's what I thought.
Yeah, that is little bit uh, like, but if you see this plot, this the lower limit plot, in this case here we are clearly seeing one peak, then here we are clearly seeing another peak.
Okay. So there are 2 graphs here, or only one graph? Only one graph.
Means this is the mean plot, and these two are for plus minus 2 standard deviation.
Okay.
So this is for plus 2 standard deviation, and the lower one is for minus 2 standard deviation.
Okay, understood.
Okay. And what is the answer for this? Generally, the hip joint force is maximum during when the hip joint force is maximum.
Is it A?
No, it is D. So there are some data from the literature, like you can compare when standing up, the hip joint reaction force is less than 200 percentage, and while sitting down, it is also less than 200 percentage. And while staring up, it is around this 260, and for normal walking, it is around 240. So maximum is for stare up, D.
Okay.
Okay, next question. Hip flexion moment is maximum at which phase of normal walking? Yes, C is correct. So here you can see hip flexion moment is maximum in during the 60 percentage of gait cycle, and during the 60 percentage of gait cycle, it is this toe off. So option C is correct. And last question, the physiological cross-section of muscle. What happens with increase in penetration angle? So we have already seen this, it decreases. Yeah. Okay, now I will discuss about stress and strain. So what is a stress? Stress is the internal force per unit area generated within a material when it is acted by external forces. So you can see this bar is getting pulled by the axial force P. So if we take the section here, then we can see because of the axial force, applied force P, there are some stresses which are getting produced inside the material, and the formula for stress is given by force divided by area. Area is the cross-sectional area. Okay, so this is the definition of stress, and strain is
the P that we are applying, is it similar to the one given in formula? Sigma is equal to P by A. A is area, right? So
yes.
P is similar to what we are applying in the front.
Same, yes, same force, yes.
Okay.
And strain is when we are applying the force P, its length will increase because of the applied load. So strain is the change in length divided by the original length. Now stress strain diagram. So for any material, we can generate this stress strain diagram by doing the tensile test using some UTM machine, universal tensile machine. So what we do, we place this specimen, we place some dog bone type of specimen in the machine, and we apply load. We apply the tensile load, and from that experiment, we get force versus the elongation plot. So from this force versus elongation plot, we can get this stress versus strain by dividing the force with area and dividing the elongation with the length, initial length. So when you do the experiment, then there is one region which is called elastic region. In this, force will be linearly proportional to the elongation. This is coming from the Hooke's law, which says this stress is directly proportional to strain. In the elastic region, but there is a point in which this material attains its plastic state, and the means it can't recover its in the elastic region is the material can get back to its initial shape, but after attaining the plastic after crossing the elastic region, the material is permanently deformed and it can't recover, it can't get back to its initial state. So we call this point as yield strength, where this material gets changes its property from elastic to plastic state. So after attaining this yield strength, its strength increases. And this region is known as strain hardening, the phenomenon because of which this strength increases. So here means there are some dislocations in the within the material. So because of the applied load and the plastic property, those dislocations align, and they they resist the applied load. So for producing the deformation, we need to apply more load. Load. So that's why this F increases, force increases, and at a step comes when this force attains its maximum force that can bear that can be applied for that material, and this point is known as ultimate strength. Means this strength value is known as ultimate strength, and after going to the ultimate strength point, the necking starts. So in the necking, the shape of the material becomes like this. Means one necking like appearance occurs at the center of the specimen. So this region is necking, and finally a point comes when this material gets fractured. This is the fracture strength.
So strain is a change in length, or is it a fraction change, something like that? Strain.
Change in length, yes.
Uh, so as our length is increasing, that means our material is becoming harder in the strain hardening region.
Yeah. In the strain hardening, it is becoming harder. Yes.
Shouldn't it become weaker, like more stress you apply as the length is increasing? Because increase in length, and it is also hardening at the same time.
Strain hardening is coming not from the length, but because of the applied load. Here is some grain structures inside the material. So
Yes.
those grains, like after this yield strength, those grains means they align, like assuming this is one layer, this is another layer. So means the layers of the materials, they stack up one above the other, and they act like a resistance to the means they resist the force which we are applying. That's why we need to apply more load to overcome this force, and means for elongating the material specimen.
Okay, sir. So it's
That's
because
why
of the
it is.
material property.
Yeah. So it is this part is coming from the material science. So
Okay.
yeah. And the proportionality constant in that means the tangent of the angle subtended by the linear part of the curve with the strain axis is known as the Young's modulus of the material. So from this stress strain plot, we can determine the Young's modulus if we get this stress strain plot. Okay, now there is one simple problem from the stress concept. So here, strain gauge is located at C on the surface of bone AB, and the average normal stress in the bone is 3.8 megapascal when the bone is subjected to 1200 Newton forces as shown. Assuming the cross section of the bone at C to be annular, and its outer diameter is 20. Now we need to determine the inner diameter of the bone's cross section at C. So formula for stress is force divided by area. So here force is given 1200 Newton. And what is the type of the cross section? Type of the cross section is annular. That means this is the bone. So the outer diameter is given and we need to determine the inner diameter. So what is the area for this cross section? Area will be pi by 4 DO square minus DI square. DO is the outer diameter and DI is inner diameter. So if we put the stress value is 3.8 Pascal and force is 1200 Newton. We'll take 4 for the numerator. Pi outer diameter is 25 square minus. So here I am not converting this megapascal into Pascal because I am taking the stress unit megapascal, force unit Newton, and the distance or length unit in mm. So if we do this, then we'll get this inner diameter unit, means inner diameter value in terms of millimeter. So if we solve this, we get 402.08. Now from here, pi square is 222.9. From here, 14.9 mm. Okay, this is the answer.
So how did you took the area of Anura's doing like that? What's your logic there? Pi by 4 and
Yeah, what is the area for a circle?
for it is pi r square, right?
Pi r square. Yeah, I am taking it in terms of diameter. So pi r
So,
square. If we
so
put r equal to d by 2,
yes.
pi d square by 4, right?
Yes, 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 yes. Do that. Square by 4. Okay. And they simply subtract outer from inner from outer.
Yeah, yeah. This is the diameter for the outer circle. Now there is one more circle which is inside. So we have to subtract the area of the inner circle. Then we'll get this kind of bone.
So you took the pi by 4 common out and then
Yeah,
calculated.
yes,
That.
yes, yes, yes.
Okay.
I have taken pi by 4 common, and so d naught square minus di square.
Okay, sir.
Okay. So we have seen the stress as two types of stress. One is the normal stress, and another one is the shear stress. Normal stress is when the force is acting perpendicular to the plane, and so if the force is acting like this, then this is a normal stress, and when the force is acting tangential to the plane, it is a shear stress. in both cases, the magnitude is same, F divided by area. So shear stress is represented with tau, and normal stress is represented with sigma. Now stress tensor. So stress is a second order tensor, and stress tensor gives information about magnitude and two directions. The two directions are the direction of force and the orientation of the plane it is acting. And for a 2D system, there are 4 components of stress, and for a 3D system, there are 9 components of stress. So you can see this is the 2D, two-dimensional state of stress, and this is the three-dimensional state of stress. And here, like sigma xx, the first index, it refers to the plane, means the plane on which it is acting, and it refers to the direction. Do you have any doubt?
No, sir.
Okay. Now, components of stress tensor. So it has 2 components. One is hydrostatic and one is deviatoric. Like we can write this state of stress in terms of hydrostatic and then deviatoric part. And hydrostatic part causes this engine volume, and deviatoric part causes this engine shape. And
Sir, but change in volume automatically will cause a change in shape. Why there are 2 parts, like 2 different components of stress?
yes. So you can see in the hydrostatic part, there are no shear stress. Means the always the stress will act perpendicular.
Okay.
So what is the shape? Shape is the rectangular shape, right?
Yes.
So it will remain always rectangle.
Okay. So it will expand, but it will always remain.
Yeah, the shape will remain same.
Okay.
But because of this deviatoric part, means it is getting tilted.
Yes, sir.
Okay.
Understood.
So this is the hydrostatic, and this is the deviatoric. So now there is one problem. For this state of stress, we need to find the hydrostatic and the deviatory component of stress. First, we'll write this stress in terms of matrix, two-dimensional matrix. So we have stress equal to sigma xx, tau xy, sigma yy. And here, sigma xx, this is the x direction, this is the y direction. So in this problem, sigma xx is given 16, and tau xy 60. But here, tau xy, for tau xy, if it is means upward, then it is positive. If it is downward, then it is negative. So it is minus 60, and it is also minus 60.
Sir, how did you determine the x and y coordinates? Like they are not given which component is x and which component is y.
You can assume any, like you can assume either, you can assume this direction x, this direction y. So it is up to you. So I am assuming this direction, this horizontal direction is x. Okay, and this sigma yy is minus 48 because it is acting in the downward direction. So we have got the sigma matrix. Now the hydrostatic component is this is the hydrostatic component. So we need to first find out the sigma m. Sigma mm is x plus yy divided by 2. 16 minus 48 is minus 32 minus 16. So the hydrostatic component is minus 16, 0, 0, minus 16. Okay, because it is sigma m, 0, 0, sigma m. And the I will write here. Deviatory component. It is sigma xx minus sigma m tau xy sigma yy minus sigma m. If we put the sigma xx is 16 and sigma m is minus 16. So 16 minus minus 16 will be 32. Tau xy is minus 60. And sigma yy is minus 48. And it will be minus 48 plus 16. It will be minus 32. Okay.
Okay.
Now stress transformations means you can see in this means in this case this is the x direction and this is the y direction, and stress are means the state of stress is given for this two-dimensional element. Now,
Sir, in the previous example, do we have to solve the matrices or we leave them as that?
yeah, no, no, you don't need to solve. Like here, it is defining hydrostatic part is defining as a matrix, and deviatory is defining as a matrix.
Okay.
Yeah, means it has 4 components. The hydrostatic part. What does this represent? This represents sigma xx. Then this represents tau xy, sigma yy.
So we only have to find them, not actually.
Yeah, you only need to find the component, not you don't need to find out the value of this matrix.
Okay, sir.
So in this case, stress transformations means this is the initial state of space is given. Now, if we are rotating this rotating this element by an angle theta in the anticlockwise direction, then its new position will be something like this. Now we need to find out the components along this x1 and y1 direction. So, like these components are given, formulas are given in your slides. Like the sigma x1 is given by this, tau x1 y1 is given by this, then sigma y1 is given by this. Now I will do the derivation part. So how these equations are, means how we get these equations. So I will assume a triangular element here. This angle is theta. So I will draw the element here. And in this element, this direction is x1, and this direction is y1, and this is the direction of x. This is the direction of y. Let us take the area of this the slant part A. Now we will use the equilibrium equations, which are summation f x1 0 and summation f y1 is 0. So for that, we need to find the force component which will act along the x1 direction. So you can see this sigma x1 is acting in the x1 direction. So here it is sigma x1, and area is A. So stress multiplied by area, we are getting the force. And tau x1 y1 into A1. This is the force along the along the y1 direction. And sigma y1 will act on this sigma y1, and we have assumed this area is A. So this area is A cos theta, and this bottom part area is A sin theta. And tau, sorry, this should be sigma y. And this is tau yx. A sin theta. And this is sigma x A cos theta. And this is tau xy A cos theta. Now we need to do this equilibrium along the x1 direction. So first we will write along the x1 direction this sigma x1 dot A, and what will be the component of this sigma x A cos theta along the x1 direction will be, this angle is theta. So it will be minus sigma x a cos theta dot cos theta and component of this tau xy a cos theta will be this is theta, so along the x1 direction it is minus tau xy a cos theta dot sin theta and sigma y a sin theta, component of sigma y a sin theta will be this is theta, it will be minus sigma y a sin theta and component of this tau xy a sin theta will be cos theta is 0. Okay, now we will solve this. So we can cancel a from both the right hand side and left hand side. A will be cancelled out. I'm writing here sigma x1 minus sigma x cos square theta and minus tau xy sin theta cos theta minus sigma y sin square theta See, in the formula, we need to find these theta terms in terms of cos theta and cos 2 theta and sin 2 theta. So here we need to use, like we know that sin 2 theta is 2 sin theta cos theta and cos 2 theta is cos square theta minus sin square theta divided by 2. Okay. So here we will use sigma x1 equal to sigma x plus sigma y sin square theta plus tau xy sin theta cos theta and from this equation we need to substitute the cos square theta in terms of cos 2 theta. So what is cos 2 theta? is, I think. Okay, from this equation, cos square. And we can write sin square theta as 1 minus cos square theta. So it is 2 cos square theta minus 1. So what is cos square theta then? 2 cos square theta. 2 cos 2 theta plus 1. Cos square theta is 2 cos 2 theta plus 1 divided by 2. And the sin square theta is 2 cos 2 theta minus 1 divided by 2. So now we'll substitute sigma x as sigma y divided by 2. And we can write 2 sin theta cos theta as sin 2 theta plus tau xy sin 2 theta. From here, so from here what we'll get, it will be 1 minus cos 2 theta. Okay. Now if we take this 1 by 2 common, then it is sigma x plus sigma y, and one more term, we need to take sigma x minus sigma y. Okay, I have done a mistake here. There is no 2. There is no 2. Okay. So there is no 2 here. Okay, now we have got that expression. here sigma x plus sigma y by 2, sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Okay.
Why are we shortening it? The first, when we first accounted our first expression, we can calculate sigma x1 from that only, right?
Yeah, from this.
Yes, yes, that one.
Yes, I am calculating using this only. Like I have taken these terms to the right side and substituted this cos square theta in terms of cos 2 theta, and they simplified
Okay.
the all the parameters.
Simplifying
Yes.
it. Okay.
Yes. So from this summation f means by doing the equilibrium along the x1 axis, we have got the sigma x1. Now if we do this second summation f of y1 is 0, means if we do the equilibrium along the y1 axis, then we will get this second expression. We will get the equation for tau x1 y1, and for the sigma y1, we need to substitute theta by theta plus 90 degree in this expression. Then we will get the sigma y1. So like this, we have got all the equations for the stress transformation step.
Okay.
So is it clear? Okay. Now there is one simplified form, like we can use the matrix form also for doing the calculations related to stress transformations. In this, simply we can use this equation, like we can use this rotation matrix R, and for getting the transform state of stress, and the rotation matrix is given with this. And note that here theta is considered in the anticlockwise direction. So theta is in this direction. If the theta is in clockwise, then this theta will be negative, and in this case theta is positive. Okay, now there is one problem. For the given state of stress, determine the normal and shearing stresses after the element shown has been rotated through 25 degree clockwise. Can you try to solve this problem?
Sorry, sir, but I'm from non-engineering background, so it's really hard for me to solve it.
Okay. Don't worry, I will do it. Like first, we need to write the stress matrix here. So here, sigma xx, tau xy. So here given sigma xx is minus 40. Again, I am taking this horizontal as x direction and vertical as y direction. Sigma xx is minus 40 here. Tau xy 20 is 20 and sigma yy is 60. Okay, now we will solve this problem using this matrix formula which is given. So we need to find sigma dash is r sigma and if R transpose and R is cos theta sin theta minus sin theta cos theta. And see, in this problem, it is given we are rotating the element in clockwise direction. So here theta will be negative. So here cos minus theta sin minus theta. Okay, this is R matrix. Then sigma matrix is minus 40, 20, 20, 60. And R transpose matrix is cos minus theta sin minus theta minus sin cos minus theta. Now cos minus theta is cos theta and sin minus theta is minus sin theta. Here it will become plus sin theta. Theta. 60 cos theta sin theta. Now we'll substitute theta as 25 degree. So I'm directly writing, I will put cos 25 here. So cos 25 is 0.91 and minus sin 25 is 0.42. Okay. 0.42, 0.91 minus 40, 20, 20, 60 and 0.91, 0.42. Now we'll do the matrix multiplication. So in matrix multiplication, we multiply this first row with the first column and we add rows. Now I'll show you how to do the multiplication. So first we'll do these two multiplications. So first element will be minus 40 into 0.91 minus 20 into 0.42 and the second element will be minus 40, 0.42. So I am getting the first element by multiplying this first row with this first column. So I got this element. Now for the second element, I will multiply the first row with the second column. Then I will get the second element. Okay. Plus 20 into 0.91. And for the for the second element of the second row, I will multiply this second row with the first column. It will be minus here. 20 into 0.91. 16 into and for the fourth element 20 0.42 0.91 This will be 0.91. Now I will find out this matrix. This is minus 44.8. Minus 1.4. Seven. $63. Now I need to do this multiplication of these two matrices. So it will be minus 0.91, 44.8, minus 0.42 into 63. 42. 44.8 plus 1.42 1.4 plus. Now if we do this, minus 43.7, $27.7, 12.4, 56.7. Okay, this is the answer. And this is the transformed state of the stress after rotating it with 25-degree clockwise. Like this, you can solve the problem.
So when you first multiply like first row with first column, there is a plus sign in between, or it is always a negative sign.
Yeah, there is plus sign, but here the negative sign is coming from this minus 0.42, right?
But conventionally there is a plus sign, right?
Yeah, plus sign, yes.
Okay.
Now there is one more concept, which is principal stress. So what is a principal stress? The principal stresses are the maximum and minimum normal stresses in a state of stress at a point. And These stresses act on the principal planes defined by the principal directions, and their shear stresses are absent. So means in the plane in which there is only the normal stress and there is no shear stress, then that normal stress is a principal stress. Like for this example, you can see there is only normal stress which is acting on this plane. There is no shear stress acting. So this sigma 1 is a principal stress. And how to get the expression for principal stress? So since there is no shear stress, so we'll equate this shear stress component with equal to 0. From this, we'll get this expression tan 2 theta tau xy divided by sigma x minus sigma y divided by 2. If you equate this equation equal to 0, so from here we can get the means after we get the tan 2 theta, we can get sine 2 theta using trigonometric relations and cos 2 theta. And if we substitute this sine 2 theta cos 2 theta in this expression, then we get this equation. Sigma 1 2 is sigma x plus sigma y divided by 2 plus minus square root these terms. So like this, means the derivation is kind of like this. First, we estimate this sine 2 theta cos 2 theta, and we substitute this into the sigma x1 equation, and from that equation we get the sigma 1 2. Sigma 1 2 are the principal stresses. Okay, now principal stresses as eigenvalues. So we know that stress is a tensor, and for 3-dimensional it is a 3x3 matrix, and for every matrix, means for 3x3 matrix there are 3 eigenvalues and 3 corresponding eigenvectors. These eigenvalues are the principal stresses, and the corresponding eigenvectors are the corresponding principal stress directions. Now we can represent the means this is the representation for eigenvalue problem. Since it is a stress is a 3x3 matrix, so we can represent the stress means in terms of this eigenvalue problem like this. And if we solve this, if we solve for the eigenvalues of this equation, then we get the values for the principal stress and the values for this n1, n2, and n3, which represent the direction cosines for the principal stress directions. So solution of the determinant results in a cubic equation that can be solved for the 3 roots corresponding to the 3 principal stresses.
So what if there are also shear stresses, like shear forces also there?
No, for principal stress there is no shear stress. Like shear stress is 0.
Yes.
There are only normal stresses. Yes.
So they don't come into equation here because by definition principal stresses only involve direct stresses, like no
Yes.
shear
Yes.
stresses.
Yes. So this is the characteristic equation of a state of stress, 3-dimensional state of stress, and the coefficients of this cubic equation are known as stress invariants. And here you can see the first invariant is given by this summation of all the normal stresses in the x, y, and z direction, and the second invariant is given by this expression, and third invariant is the determinant of the 3-dimensional matrix. And to to calculate the principal directions, we need to solve this equation. Here n1, n2, and n3 are the direction cosines of the principal plane. Now we'll solve one problem related to this. So you can see this is a three-dimensional state of stress is given. Now we need to find the principal stresses for this state of stress. So we can write sigma is equal to, so three-dimensional state of stress is sigma xx, tau xy, xz. So it is 80, tau xy is 20, tau xz minus 50, 20 minus 40, 30, minus 50, 30, and minus 40. So this is the state of stress given. Now we'll solve, we'll estimate this invariance. We'll estimate the first invariant, second invariant, third invariant. Then we'll solve this equation. So the first invariant is I1 sigma xx, sigma yy, sigma zz. 80 minus 40 minus 40. So we are getting first invariant is 0. Now the second invariant is sigma xx plus sigma yy tau yz plus sigma tau xz sigma xx. So we'll substitute sigma xx is 80, 20, 20 minus 40 plus minus 40 tau yz is 30, 30 minus 40 minus 40 minus 50, 80. Now we need to find the value of this matrix. So it is 80 cross minus 40 minus 20 cross 20 minus 40 square minus 30 square plus minus 40 cross 80 minus 50 will be plus 50 square. This value will be minus 8600. Okay. And the third invariant, is the determinant of the three-dimensional matrix. I3 is 80, 20, 50, 20 minus 40, 30, 20 minus 40. So its determinant is E minus 40 cross minus 20, 20 cross minus 40 minus 30 cross minus 50, 50 30 minus 12, 80, 40 square minus 30 square minus 800 plus 1500 minus 50, 600 minus 2000. If we do this, it's coming 112000. Okay, now we'll substitute this I1, I2, and I3 in this characteristic equation, which is sigma cube minus I1 sigma square plus I2 sigma minus I3 is 0. So we have got I1 is 0. So it will be sigma cube plus I2 we got minus 8600 sigma, and I3 we got minus 112000. Now to solve this equation. So if you have a scientific calculator, then you can solve the cubic equation directly using the scientific calculator. But unfortunately, my calculator, that function is not present. So, or you can use any other coding like MATLAB. Doing any other programming, you can solve this. So if you solve this, then you will get the sigma 1, sigma 2, and sigma 3, which are the principal stresses. Okay. Yeah. So have you understood the problem, or if you have any doubt, you can ask.
Yes, sir. I understood the concept of science side.
Okay.
Still requires some mathematical part.
Yeah, yeah.
So if you can suggest me like bare minimum mathematics I should know for this course that I will need to.
You are from which background? Like your undergraduate is from which background?
My undergraduate is from BPharm and I'm currently doing masters in medical devices. And,
Okay, okay, okay. Yeah, so I can understand, like, but if you attend my tutorial lectures, then means I explain all the mathematical concepts which are required for this course.
okay.
So if you attend, if you have missed my previous tutorials, so you can watch those videos. Those videos are available on the YouTube.
Okay. So mathematics outside of this, like these examples, will not come for course.
Yeah, means these are the sample problems. In the exam, these kind of problems will come.
But
And
the method for solving them will stay same, right?
yeah, method will be same. And in the means in the course also, the professor is also explaining some concepts, some mathematical problems. He has also solved some problems, so you can watch those problems. And if you face any doubt, you can ask. You can mail to me, or you can post in the forum, NPTEL forum, the group discussion forum. You can post your queries there.
Okay, sir. Thank you, sir.
Okay. So this was all for today. So again, I will take the next tutorial on the next Friday, 26 September. And you can mail to me, like, if you have any problem.
Yes, sir.
Okay. Okay. Thank you.
Thank you, sir.
Yeah. Thank you.